All right, picture this. Imagine a system that serves billions of requests every single day to users spread across literally every continent on the globe. Now, imagine that this exact same system has to successfully return a result in under 50 milliseconds every single time. It sounds like some impossible theoretical benchmark, right? But it's actually running right now. You know when you log into GitHub, Stack Overflow, WordPress, or Discus? Think about the profile picture you see sitting right next to your username. It was very likely not stored by that site at all. Instead, it's almost certainly being fetched from one massive, hidden, global service whose entire job is just mapping an email address to an image. That service is Gravatar. Welcome to This Explainer. Today, we're deconstructing the architecture of Gravatar, the hidden avatar engine. Here is our blueprint for today. We'll start with the hidden avatar engine itself, then move into identity and edge caching, stateless auth and decoupled uploads, database schema and partial indexes, atomic state and architecture, and finally, operating at global scale. Okay, part 1, the hidden avatar engine. Here is the absolute biggest lesson you can take away from this entire explainer. The architecture you choose is dictated by the shape of your traffic, not your feature list. Just think about the sheer asymmetry of the traffic here. Hot reads make up 99.9% of the volume, almost all of it, and these read paths share virtually nothing with the write paths. When a principal engineer looks at a system like this, they don't immediately start sketching out a database schema. They realize that the 4 main paths, hot reads, cold reads, uploads, and mutations, have to use entirely different domains, completely different storage, and have totally different consistency guarantees if they are going to scale. Moving right along to part 2, identity and edge caching. So, how do we actually know who is asking for what without totally bogging down the network? Well, for our first pillar, the key is that identity is purely derived. A user's public identifier isn't some sequential database ID or a bulky UUID. It's an SHA-256 hash of their email address. This is brilliant because a website integrating Gravatar needs zero network coordination. No database lookups at all. They just compute the hash right there on the client side and construct the URL. Boom, it's a one-line dependency. It's kind of like having a public mailbox that's addressed entirely by your fingerprint. And because that hash is totally stable, we can lean heavily into Pillar 7, the Content Delivery Network, or CDN, facade. I cannot stress this enough. This is the single most leveraged optimization in the whole design. The CDN sits right in front of the API, absorbing all those hash-based read hits at the edge. Sure, a cache miss has to go back and fetch from the origin, but the next million requests for that exact same hash, they are served locally from an edge node right near the user. You are literally turning a single region service into a globally distributed one with a simple DNS change. Let's hit part 3, stateless auth and decoupled uploads. Let's pivot for a second to that super rare upload path. How do we securely authenticate a user and ingest a huge image file without absolutely choking our API servers? This brings us to Pillar 2, and it shows exactly why public key cryptography is an absolute game changer. Think about it. If we used a shared secret, every single microservice would have to phone home to the auth service just to validate a token. That's a massive system-crushing bottleneck. Instead, by using adjacent web token, or JWT, backed by public key cryptography like RSA, the photo service can verify tokens locally. The auth service holds the private key to sign the token, and everyone else just holds the public key to verify it. That completely removes the auth service from the hot path. Zero network calls to verify. It's a beautiful thing. Once they're authenticated, we bring in Pillar 3, decoupled uploads. We absolutely do not want users uploading 5-megabyte vacation photos directly to our API and holding up valuable server connections. Instead, the client just asks the API for permission. The API then hands back a pre-signed S3 URL. Think of it like a temporary VIP pass. The client then takes that pass and uploads the heavy image bytes directly to S3. The API server, it only ever handles tiny metadata requests and literally never touches the actual image bytes. The savings in CPU and bandwidth are just staggering. Next up, part 4, database schema and partial indexes. Let's talk about the mutation path. For those extremely rare moments, we're talking maybe once every couple of years, when someone actually bothers to update their avatar, how do we structure the database? Normally, textbook engineering says you want a normalized schema to act as a single source of truth, which requires a table join to go find the active photo. But remember our crazy traffic shape? Read traffic dominates write traffic 10,000 to 1. Because of that, Pillar 4 says a denormalized schema is actually way better here. By storing the active photo ID directly right inside the user table, we collapse that expensive join into a single, blazing fast index lookup. But wait, we still have to keep track of all those other photos a user might have. Enter Pillar 5, the partial index. This is an incredible Postgres feature. It's basically a surgical optimization that lets you index only the tiny subset of rows that actually matter to your queries. By simply slapping a conditional where is active equals true onto a unique index, we are hard-coding our business invariants straight into the storage layer. If a user uploads 10 different photos over the years, only one can be active. The database physically prevents 2 photos from being active at once for the same user. And the best part? The index size drastically. If you have 100 million users, that index is exactly 100 million rows, not a billion. Moving on to Part 5, Atomic State and Architecture. So, how do we safely change that state? When you switch your avatar to a new photo, everything has to happen perfectly. For Pillar 6, we use a single atomic SQN statement that does all the heavy lifting. It uses a case condition to safely activate the new photo and deactivate the old one at the exact same time. This makes the whole operation atomic and idempotent. Without this kind of atomicity, you might hit a split second where a user has 0 active photos, or worse, 2 active photos, which, by the way, our partial index would immediately throw a fit over and reject. This query ensures strict data integrity without getting bogged down in complex locking issues. And bringing this all together for Pillar 8, just look at the strict separation of concerns across the architecture. Everyone stays in their lane. The CDN only knows about URLs and cache rules. The API strictly handles generating URLs and metadata. The database just stores those tiny metadata rows. And S3, it just blindly trusts those pre-signed URLs to handle the heavy bytes. Every single component is stripped down to its absolute minimum viable role. That means the whole system is independently scalable and, crucially, independently failable. And finally, Part 6, Operating at Global Scale. Let's leave the theory behind and talk reality. A system is honestly only as good as its ability to operate at a massive global scale, especially when things inevitably break. When we break down the service level objectives, or SLOs, the massive read path demands higher availability. We're talking 4 nines, 99.99% uptime, and much lower latency than the rare write path. Because we completely decoupled them, our primary database could literally be taken offline for maintenance, and the read path, it would still easily hit that 99.99% uptime. Of course, a proper engineering review demands that we handle failure gracefully. We are constantly tracking those CDN cache hit ratios per region. If the database drops, no problem. We just gracefully fall back to serving stale data from the CDN, and the user never even notices. If an S3 upload succeeds but the database write fails for some reason, we have background reconciliation jobs to clean up those orphaned objects. And naturally, we deploy everything behind feature flags, so if something goes sideways, we can roll it back instantly. By breaking down Gravatar, you're actually looking at the very DNA of how the modern web scales. You see these exact same patterns everywhere, in GitHub social cards, Reddit thumbnails, and Slack avatars. So as we wrap up this explainer, here is my question for you. How will you apply these transferable patterns, like content-addressable hashes, pre-signed URLs, and partial indexes, to scale your own architecture effortlessly? Think about it. Thanks for joining me, and I'll catch you in the next explainer.